Graphing exponential functions. It's useful when graphing exponential functions to have a sense of what an exponential function's graph looks like the basic one, before you go into graphing more complicated ones. So if you have an exponential function of the form f of x equals a to the x, a is a constant, like 2, 3, something like that, then if a is bigger than 1, the graph looks like this. So an example would be something like f of x equals 2 to the x. The basic graph here looks like something like this. Now there's an asymptote right here along the x-axis, but we don't always draw it. Now you can figure out what some of the specific points are on this graph by making a table and plugging values in. So for example, if we want to know what the output is when x equals 0, we can plug it in to get 2 to the 0 is 1. We can plug in another number, like maybe 2, to get 2 to the 2 equals 4. And that tells us that we have some specific points here, like 0, 1 and 2, 4 on the graph. But it's a good idea to memorize the general shape of an exponential function, a to the x, where a is bigger than 1. It looks like this. Now, if your exponential function has base a that is in between 0 and 1, so it's a fraction or a decimal smaller than 1, then it actually has a shape that looks like this instead. So it goes the other way. So an example would be something like f of x is equal to 1/2 to the x. So the graph of this one is going to look like this instead, where there's, again, an asymptote along the x-axis that we don't always draw. And then if you want to start figuring out what some specific points are on the graph, you can make a little table and plug numbers in for x, like for example 0, or something like 2. And so then you can mark off what a couple of specific points are if you want to. Okay, so I would suggest memorizing the general shape of these two. Now, how do we graph some specific exponential functions? Let's graph the function f of x equals 2 to the x minus 3. Now, my favorite technique, or the way that I do this, is I identify what I call the toolkit function. So the toolkit function here is like sort of the basic function that you can then transform or do transformations to get the one that you're given. So I'm going to say our toolkit function is y equals 2 to the x. And I can graph 2 to the x very quickly because I know the general shape is like this. So let's draw it in a light color. I know the general shape is something like that. And then I can get it a little bit more accurately by plugging some numbers in and plotting specific points. So for example, if I want to know what the graph of 2 to the x looks like, I can plug a couple numbers in, like 0 to get 2 to the 0 is 1, and maybe like 1 to get 2 to the 1 is 2, 2 to get 2 squared is 4, and then I can come over to my picture and plot some points like 0, 1, 1, 2, and 2, 4. And then I can sort of fill in the rest using what I've memorized, and that's like the general shape of the 2 to the x function. So I've sort of memorized the general shape and then plugged in a couple points to get a more detailed graph. Now, what do I do with this? Well, I can use this graph to figure out what the graph of f of x equals 2 to the x minus 3 is. How do I do that? Well, this graph here of f, it's just the toolkit function, but shifted to the right 3. So shift right 3. So I'm going to take the blue graph and I'm going to take every single point on here and I'm going to move it to the right 3. So I go 1, 2, 3. I take this next point and I go 1, 2, 3. I take this other point and I go 1, 2, 3. And if I do that with every single point, I get a new graph that's the blue one, but shifted to the right 3. And so I'm using the toolkit function y equals 2 to the x, and then shifting it right 3 to get the function that we want the graph of. If you want to know what some of these specific points are, you just have to do this accurately enough so that you can, count over and see where they are. So this point right here is at 3, 1. You can see it in the picture. This point right here is at 4, 2. And then this point up here is at 5, 4. Okay, let's look at another example. How do we graph f of x equals 2 to the x minus 3? Well, we still have the same toolkit function, so our toolkit is y equals 2 to the x. And we've seen that that graph looks something like this. We just graphed it. So we know that's what y equals 2 to the x looks like. And then if I subtract 3 from the entire function, so if I do 2 to the x and then minus 3 on the outside, what's going to happen is our new function will be y equals 2 to the x shifted down 3. So all we have to do is take every single point on the blue graph and move it down 3 to get f of x. So I take this point and I go down 1, 2, 3. I'm counting down on the grid. I take this point up here and I go down 1, 2, 3. I take this point right here and I go down 1, 2, 3. And then I can just fill in the rest of the graph. Now, we want to account for the asymptote here. So there's this asymptote right there at the x-axis. Now in the example that we did previously, let's scroll back up to it. We also had an asymptote here, but we were shifting our graph to the right. So when you shift your graph to the right, the asymptote also shifts to the right, but it doesn't actually move anywhere. Now in this example, if we shift our graph down, our asymptote is actually going to shift down as well. So the asymptote is going to go down 1, 2, 3. The asymptote also shifts. When an asymptote that's horizontal shifts right, left, it doesn't move, but if it shifts up, down, then it does move. So let's fill in the rest of this picture here. I take the blue one and I move every single point down 3 to get something that looks like this. So I'm using toolkit functions and shifting them right, left, up, down, just like you've done with other functions. Okay, let's look at another example. We're going to try to graph f of x equals negative 1/3 to the x plus 1. So for this one right here, our toolkit function is, so the toolkit is y equals 1/3 to the x. Now we know the general shape of an exponential function when the base is less than 1 goes the other direction. So by that I mean it's going to look something like that. It looks something like that. I can fill in some exact points so I can figure out more accurately where it is by plugging some numbers into 1/3 to the x. So I'm going to erase this and we're going to make a little table and we're going to plug in a couple of values for 1/3 to the x. For example, if I plug in 0, I get 1, and maybe I'll plug in a negative. So if I plug in -1, I get 1/3 to the -1, which is 1/1/3, or 3. So a couple of exact points would be 0, 1, and then -1, 3, which is like right there. And then we know the general shape is that it goes it curves this way with our asymptote on the x-axis. So this is our toolkit function and we'll do transformations to it to get f. Okay, now what transformations do we do? Well, if I put a +1 up here with the x, then we need to shift this to the left 1. So this needs to go left 1. So I take every point here and go to the left 1. Now, the asymptote is horizontal, and if you shift it to the left 1, it just stays in the same spot. So our new graph is like the old one, but shifted left 1. Then if I put a negative in front, right here, that's going to reflect this graph over the x-axis. So we need to now reflect over the x-axis. So let's find a way to squeeze this in here. So we reflect over x-axis. And so I take every point on the purplish pink graph and I reflect it over the x-axis to get something that looks like this. And this is our graph of f of x equals -1/3 x plus 1. Now, if you want to mark off where a couple of exact points are, what you can do is just make sure you're careful where you plot your points in your grid. And so I kept track of 2 points. I had this one at 0, 1, and it moved to the left 1, and then it got reflected. So now it's at -1, -1. And then I also kept track of the point -1, 3. It moved to the left 1, so now it's at -2, 3, and then it reflected over the x-axis. So at this point, it's at -2 and then -3. So I would suggest keeping track of 2 points at least when you do these. Okay, let's look at one more. How do we graph f of x equals 3 times 2 to the x? So in this case, our toolkit function is y equals 2 to the x, which we've seen a bunch of times at this point. So we know that that graph goes through 1, and then it has 1, 2 on it, and it has 2, 4 on it. And then you can plot more if you want, but generally just like 2 is enough. We know the general shape, and we know that it goes like this. Then there's also an asymptote here. Okay, now what happens when I multiply this toolkit function by 3? So what happens when I do f of x equals 3 times 2 to the x? Every y value is multiplied by 3, so that's that sort of transformation. So what we want to do is multiply each y value of y equals 2 to the x by 3. Here's what I mean by that. If our graph has 0, 1 on it, and 1, 2 on it, and 2, 4 on it, I'm going to take every single y value and multiply it by 3. So I'm going to multiply every y value by 3 to get new y values. In other words, I'm going to have 0, 1 goes to 0, 3 times 1, or 0, 3. And then I'm going to have 1, 2 go to 1, 2 times 3, or 1, 6. Let's write that down on the side. So 0, 1 goes to 0, 1 times 3, or 3. 1, 2 goes to 1, 2 times 3, or 6. And 2, 4 goes to 2, 4 times 3, or 2, 12. So every y value gets multiplied by 3. Now I can't fit 2, 12 in my picture because I didn't give myself enough room. But if I multiply every y value by 3, I get a graph that has a y-intercept that's higher up. So notice that this y-intercept's up here at 3 now instead. And then also it's sort of like the graph is like stretched up. It's like more steep right here. Okay, now this green one right here is our graph of f. So the key way to do these graphs of exponential functions is to, let's summarize. Memorize what a general exponential function looks like for a is bigger than 1 or a is less than 1. And then use toolkit functions and transformations to graph more complicated versions of these.